You probably learned a matrix is a table of numbers, true, and about as useful as calling a violin a wooden box with strings. Inside a neural network, a weight matrix has one job. It transforms data. Input goes in, something geometric happens, the result moves forward. The question is, what geometric thing? Take a 2 by 2 matrix and a vector, y equals to ax. Written out, it's just weighted sums. Nothing geometric there yet, but rewrite the exact same equation by columns, and then you can see it. The output is built from the columns of A, weighted by the input. The matrix isn't producing numbers, it's choosing where vectors can land. Its columns define a new coordinate system, and multiplying by A re-expresses your input inside it. Here's the problem. You can see it's doing something geometric, but you can't cleanly say what. Is it rotating, stretching, or collapsing a dimension? For a 2 by 2 matrix, you might be able to guess. But a very large matrix inside a transformer, there's no chance. And that's where SVD comes in. The singular value decomposition says every matrix transformation, however complicated, breaks into 3 simple steps. A equals to U sigma V transpose. Any transformation is just rotate your input, stretch or shrink along each axis independently, then rotate the result into place. That's it. Rotate, stretch, rotate. The SVD finds the exact rotations and the exact stretch factors for any matrix you hand it. Here's the picture that makes it click. Take the unit circle, multiply every point by A and plot where they land. Then trace an ellipse. And that ellipse is the SVD made visible. The axis directions came from U. The axis lengths are the singular values from sigma. The original directions that stretched into them came from V. So the singular values, the diagonal of sigma, measure how much the matrix distorts space along each direction. If they are all equal, the ellipse is just a bigger circle, pure rotation, uniform scale, and no distortion. But if sigma 1 is huge and the rest are tiny, the ellipse is a thin pancake. The matrix has crushed almost everything onto one direction. The second case is the villain. Let's hold on to it. So a network is a stack of these matrices. Data flows in, each one transforms it, and everything the network knows lives inside their numbers. So training has a concrete meaning. Find the right numbers to put in the matrices. They start random and useless. Training adjusts them until the network is good. Good needs a number. Give the model a task, measure how wrong it is, roll that wrongness across millions of examples into a single value, which is the loss. High loss is bad for the network. The entire goal of training is to drive that single number down. So the optimizer's job has a crisp shape. Look at the matrices and the current loss and nudge the numbers to push the loss down. That nudge is the update rule. Picture every possible setting of those matrices as a point on a landscape with height equal to the loss. Training is just walking to the lowest point. But it's foggy. The optimizer can't see the whole landscape. It only feels the ground under its feet, which way it tilts and how steeply. That slope is the gradient g, the same gradient g from the update rule. It points where the loss rises fastest, so you step the opposite way. W is your position, g is the slope, and the negative sign means downhill. And eta, the learning rate, is the stride. Fill the slope, step downhill, repeat. That's gradient descent. The great grandparent of every optimizer, including the one we're building to. So just follow the slope down, solved? Well, not quite. 2 things break almost immediately. First, the stride. Too small and you crawl forever. Too big and you leap over the valley. Even bounce up the walls and never settle. No single stride is right everywhere. Second problem is worse, and it's the one that matters. Real lost landscapes aren't tidy boughs, they're ravines. Long, narrow canyons, steep walls, a floor that slopes gently towards the exit. The slope under your feet is dominated by steep walls, so the gradient points mostly across the canyon, barely along it towards the goal. So you bounce wall to wall, wasting nearly all your motion sideways, slow, wasteful, and at real scale, it means weeks of extra training. Two ideas were invented to fix exactly this. The first one is momentum. Stop treating each step as fresh. Give the optimizer a memory. Think of a heavy ball rolling down the canyon instead of a hiker taking discrete steps. The sideways wall pushes point in opposite directions and cancel. The gentle, consistent push down the canyon accumulates. The ball builds speed in one direction that matters. So mechanically, keep a running average of recent gradients and step along that. The V is velocity, accumulated memory of where you've been heading. It's in essentially every production optimizer. And fix 2 is to use a different stride per knob. A weight matrix has thousands of individual numbers or knobs. Some get big, loud gradients, others get tiny whispers. Forcing one stride on all of them is wrong. The loud ones need small, careful steps, and the quiet ones need a boost just to move. This is Adam W. It tracks each knob's recent gradient history and gives each its own stride. The gradient G is not a bag of numbers, it's a matrix, which means it has its own SVD, its own singular values, and its own geometric shape. In practice, a gradient's singular values are wildly unbalanced. The largest can be 50 or 100 times the rest, and that's the pancake from before, now in the gradient. So when you subtract eta g, you don't update the weight matrix evenly. A few directions get hammered, the rest get almost nothing. Step after step, it compounds. Some structures in the weight matrix grow uncontrollably while others stagnate, not because they don't matter, but because the gradient never gave them a loud enough signal. Activations explode in some places, vanish in others, the system gets fragile. Adam W rescales the loud and quiet knobs, which helps. But because it can't see the matrix, it can't fix the shape of the distortion. To fix the shape, you have to treat the gradient as what it is, a matrix with an SVD. The gradient does three things: rotate, stretch, rotate. The stretching is the villain. It's what makes some directions dominate and others vanish. The rotations are the useful part. They encode which directions to move in. So keep U and V transpose, delete sigma. What's left, UV transpose, is a product of two rotations, which is itself a rotation, and a rotation can reorient vectors but never change the length. Put a unit vector in, get a unit vector out. In SVD terms, every singular value of UV transpose is exactly 1, not because we set them by hand, but because that's what pure rotation, no stretching means. This is Muon, written by Keller-Jordan and published openly in the year 2024. Not in a journal, but for a community speedrunning NanoGPT training, and it broke the record. Find the nearest matrix that introduces no distortion. That exact question has a name and a story. There was a man in ancient Greece named Procristes, a bandit who offered travelers a bed on the condition that they fit it perfectly. Too short, he stretched you on a rack. Too tall, he cut off the excess. He forced things to fit by destroying them. The hero Theseus finally killed him the only fitting way, by forcing him onto his own bed. In the 1950s, psychometricians named a geometry problem after him. Given two matrices, find the rotation that best maps one onto the other. They named it Procristes because, like the myth, it's about forcing things to fit. Except the math inverts the myth. The mythological Procristes forced the fit by distortion. The mathematical Procristes finds the nearest fit with zero distortion. That problem was solved definitively by Schoenemann in 1966. Given any matrix G, the nearest distortion-free matrix, pure rotation, no stretch, is UV transpose. That's our first dead mathematician, and that's exactly what Muon does to the gradient at every step. Keep all the directional information, strip out the magnitude imbalance that makes some directions scream while others whisper. One practical catch: a full SVD on a million entry matrix, every step would be brutally expensive. So Muon uses Newton's Coulomb iteration, 5 steps of a fixed polynomial that approximates UV transpose directly, without ever computing U sigma V separately. Fast, GPU friendly, no eigen decomposition. Remember that name, it comes back. So now we have a family: gradient descent, momentum, Adam W, Muon. They all argue about how to choose a direction, but step back and look at what they share. Every one of them roams completely open space. The only question anyone can answer is, which direction reduces the loss right now? Then they go there. No fences, no forbidden regions. That's fine usually. For most weights, go wherever reduces the loss is exactly what you want. But some matrices can't have that freedom. Some matrices must obey a rule forever, and none of these optimizers can promise that. Ask any one of them to reduce the loss but never leave the region, and they have no mechanism for the second half of the sentence. We don't just need a better step, we need an optimizer that can be told a rule and cannot break it. That's a different field, constraint optimization. When you want a matrix to always satisfy some property P, you have 3 options. Option 1, tax the violation, add a penalty to the loss, break the rule and I'll make your loss worse. You're not forbidding it, you're pricing it. Most common and the leakiest: if the model can cut its error by more than the fine, it'll break the rule and pay. The constraint is a suggestion. Option 2, project after each step. Let the optimizer step wherever it wants, then forcibly snap the parameter back into the legal region. It works, but it's jarring. Between the step and the snap, the parameter spends part of its life illegal, and the path zigzags. Step out, snap back, step out, snap back. And option 3, reset the ground. Don't tax, don't snap, rebuild the very ground the optimizer walks on so that stepping outside the legal region is simply impossible. The constraint stops being a rule you enforce and becomes part of the geometry itself. Option 3 is the most elegant and the most demanding. The first 2 bolt the rule on afterward. The third bakes it into the world. That's the one DeepSeek uses, and to build it, we need to reshape the flat space into a curved space. But what does it mean to reshape the ground? Until now, the optimizer walked in flat open space, every weight a free coordinate. Reshaping means replacing that flat field with a curved surface you can walk along but never step off. The technical name is a manifold. The cleanest example is the surface of a sphere. Stand on a globe, walk in any direction you like. Every direction keeps you on the surface. You can't accidentally step off because there's no off. The rule stay on the sphere isn't enforced, it's just true by the shape of where you are. And that idea has an origin. In 1854, in a cold lecture hall in Göttingen, a shy, sickly young man stood up to defend his place at the university. His name was Bernhard Riemann, and the lecture he gave on the foundations of geometry was so far ahead of its time, almost no one in the room understood it. One person did, Gauss, his old teacher, who was never impressed by anything. He walked out shaken. Riemann had described curved space, not shapes drawn on a flat page, but worlds curved in themselves. Surfaces you can live on and move through but never step out of, in any number of dimensions. And it was useless. Beautiful and completely useless, sitting on a shelf for 60 years, until a patient clerk named Einstein found it and used it to describe gravity. Riemann died at 39, having drawn a map for worlds that didn't exist yet, the curved world you can walk on but never leave. That's his. Now, make yourself the optimizer on this surface. You want the lowest point and you can feel the slope, but there's a wrinkle. The gradient is dumb. It doesn't know about the surface. It points where the lowers the loss, and the direction usually points through the sphere off into a space where you're not allowed to go. So walking on a curved surface takes 2 moves instead of 1. First you project, flatten the raw gradient onto the tangent plane, the local flat approximation of the surface at your feet, stripping away the part that pointed off into space and keeping only the part that moves you along the surface. Second, you retract. Take your step along the flattened direction, but because the surface curves, a straight step drifts slightly off it. So you snap back down to the nearest point on the surface. But notice what's still dangling. We have a method, project, step, retract. You don't yet have 2 things. Which matrices in DeepSeek need this, and which surface to pin them to. Answer both and something quietly beautiful happens. To find the matrices, look at the single most important idea in modern deep learning. In a transformer, every layer adds its output to a shared running total, the residual stream, and that XL plus is the skip connection, which is arguably the most important architectural idea since backprop. Without it, the training signal travels backward through 100 layers, multiplied down at each one until it's effectively 0. The skip connection gives it the highway. It flows around the layers and arrives intact. So the skip connection is a hero. But here's the thing nobody mentions. The same highway that helps gradients flow backward creates a traffic jam for information flowing forward. Picture an office with one shared notebook. Everyone writes into the same pages. By page 100, every page is 20 people's handwriting layered on top of each other. That's a deep residual stream. By layer 50 or 100, every prior layer has written into the same place. It becomes a muddy pile of everything computed so far. ByteDance confirmed this at Eclair 2025 in deep models. Adjacent layers learn nearly identical things. Layer 48 and 49, almost the same. They called it representation collapse. And notice the shape. It's the same disease as the gradient story. There, the gradient's singular values were lopsided. Here, the stream's capacity is lopsided. Early layers saturated. Late layers can't carve out the room. Imbalance across directions again. ByteDance's fix was elegant. Don't have one residual stream, have several. Keep 4 parallel streams. At each layer, 2 learnable matrices, AL and BL. Decide how that layer reads from the streams and writes back. And because they're learned, the model discovers its own routing. Maybe stream 1 carries syntax, stream 2 carries facts, stream 3 reasoning state. Nobody tells it to. So why does anything else need to happen? Because AL and BL are trained too. Updated by the optimizer like every other weight, with the same lopsided gradients. Over a long run, on a giant model, they drift into dangerous places. One stream dominates and you wasted 3, or the matrices amplify until the numbers overflow, or they shrink toward 0 and kill the early signal. At a few billion parameters, Adam W's damping hides all of it. At 100 billion plus it bites, a trillion plus it's catastrophic. And you find out millions of dollars into the run. So here are our matrices. We need AL and BL free enough to learn real routing, but constrained enough that they can never drift into those 3 disasters. That's exactly the constrained optimization problem, and we already have the method. Project, step, retract. All that's missing is the surface. So we need a surface where those failure modes are simply impossible. The choice in MHC is a set of doubly stochastic matrices, a shape called the Birkhoff polytype. 3 rules. Every entry is non-negative. Every row sums to 1. Every column sums to 1. And in plain English, each output stream is weighted average of the input streams. Mixing is allowed. Creating or destroying signal is not. Look what those 3 rules buy. Rows that sum to 1 with nothing negative make every output a weighted average, and averages can't blow up. The largest singular value is pinned at or below 1, so explosion is gone. Columns that sum to 1 mean every stream's mass is delivered somewhere in full, nothing photocopied, nothing threaded. And the identity matrix sits exactly on the surface, so the clean residual highway is always 1 point away. The paper measured it, unconstrained signals amplified about 3000-fold, on the manifold 1.6. Here's how I picture it: a postal service with strict rules. They can sort your mail into any bin, reroute it anywhere, rearrange it however they like, but they are forbidden to photocopy a letter or shred one. Whatever volume goes in comes out, just rearranged. And that's the bet MHC makes. Now the practical part. To live on this surface, we need the retraction step. After a gradient step, the matrix drifts off. An entry dips negative, one row sums to 1.1, a column to 0.9. We need to snap it back, the nearest well-behaved version of what the step produced. The fix is almost embarrassingly simple, and it comes from 1967. Sinkhorn and knob. Clip the negatives, then divide every row by its sum. That breaks the columns, so divide every column by its sum, which slightly breaks the rows, and do the rows again. Alternative about 20 passes, and it converges to a genuinely doubly stochastic matrix. No SVD, no eigen anything, just division. Sounds familiar? It should. Muon scrubs the gradient with 5 Newton school steps, chasing the nearest orthogonal matrix, a story that starts with Schoenemann in 1966. MHC scrubs the parameter with 20 Sinkhorn knob passes back onto the Bigkoff polytype, published the very next year, 1967. 2 cheap iterative scrubbers from back-to-back years, asleep for 6 decades, both woken up inside one training run. Muon controls the geometry of the update, MHC controls the geometry of the parameter. Different manifolds for different jobs. Update gets the orthogonal matrices, every stretch factor exactly 1. Routing gets the doubly stochastic matrices, mass conserved in and out. But it is the same move. Pick the surface where your Fourier mode cannot exist and project back onto it every single step. And the 2 surfaces even touch the corners of the Birkhoff polytype are the permutation matrices. The only matrices that live on both, pure shuffles. And the scale of it, out of 1.6 trillion parameters, this constraint touches maybe a few million, thousandths of a percent, but that thousandths of a percent is the plumbing. Every other parameter's information flows through. Few honest reactions. First, the math is genuinely beautiful. 2 constraints born a year apart in the 1960s, each pinning one half of training to its own manifold. The update to the orthogonal matrices, the routing to the doubly stochastic ones. The same design move discovered twice, 60 years before anyone needed it. In a field where most tricks are ad hoc, Muon and MHC feel designed. And second, some discomfort. Pinning a matrix to a specific manifold is a strong claim about what good matrices look like. That the right routing matrices are exactly the doubly stochastic ones. That any amplification in routing is always pathological. That might be true. It might be a bet that looks right today and gets revised in a year. The whole history of this field is confident claims about inductive biases turning half right. So if you wanted feed data, get intelligence, it isn't that. If you wanted use the best mathematical tools we have to build systems that work, it's exactly that. MHC is a beautiful bar of the cage. Let's see how long it stays.